This is Jonathan Magen, and you're listening to Agile Uprising, a podcast right here, right now.
Greetings and welcome to another edition of the Agile Uprising podcast. I'm your host again, Jay Hersko, and the topic of this week's episode is a unique one. This episode is going to be talking about teams through the lens of distributed systems. What the hell does that even mean, Jay? Well, it's a good thing you're all asking because I have someone here to help explain it. A good friend of mine, fellow colleague, he has a seat at the rare table of smartest guys Jay knows, Mr. Jonathan Magen. So Jonathan, thanks for joining us again. For those listeners who are paying attention, Jonathan was on a previous episode. We both got up at 4 o'clock Eastern time to interview Mark Burgess about promisers. So Jonathan, thank you so much for joining us.
It is my pleasure. Thank you for having me. Big fan of the show. Hope you know that.
Thank you. Thank you. So Jonathan, I'm not going to do your bio. I'm not going to give you an introduction because I think I would not do it a good service. So for our listeners who maybe didn't hear the Promise Theory episode or who maybe want to learn a little bit more about you, can you give us like a quick introduction?
Yeah, absolutely, Jay. So I'm a principal computer scientist, whatever that means, working in healthcare for about 7 or 8 years now. I did startups for about 5 years before that. Much like yourself, I'm a native Philadelphian, native to the Philadelphia area. I actually went to school in the Pacific Northwest, and I did my undergrad research with the Advanced OS lab at my school. So that was kind of a catch-all for people who are interested in advanced work. And while I was there, I got really passionate about distributed systems, among other topics. I'm writing a book with a colleague of mine about the actor model, which I am hoping to release for free at some point later this year. God willing, I can get myself in gear and get the first section done. Yeah.
Perfect. And yes. Jonathan is a man of many talents. One of the reasons I enjoyed working with Jonathan is we would send links back and forth to one of our stuff that was pursuant to our interest, but kind of tangential, which is where this episode came from. So the genesis of this episode is Jonathan and I were going back and forth, and I think it started with like Lojban, and the idea of creating a language. For those of you who don't know, Lojban is a human-generated language that allows humans and computers to speak the same language. So you would code in the language that you would converse. The intent being that on a long enough timeline, we would end up with artificial generalized intelligence, because we're speaking the same language. But then Jonathan and I started throwing out things like spiral dynamics. Mr. Lulu raised his head, and then holacracy came in. And Jonathan proposed, well, we should really pivot the conversation to be about distributed systems, and distributed systems as a lens, as a way to look at the world. So Jonathan, let's start off with brass tacks here. How would you define a distributed system?
All right. So there are two ways that I would describe a distributed system. The first one is not my definition, but it's better than my definition. It's a little tongue-in-cheek, and it's by Turing Award winner Leslie Lamport, who is an absolutely brilliant computer scientist. And Leslie said, a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable, right? And I love this, right? And the reason I love this is because it's just, first of all, it's so much better than my definition. My definition is, a distributed system is one where different parts of the same logical application cooperate by running in different places and possibly also at different times. That is way less pithy than, Leslie Lamport, who, of course, is such a maven, right? Now, the interesting thing is that when I say that they're cooperating, that means that two things are implied. So communication, doing things, and computation, right? So speaking and doing things, talking and doing things, communication and computation, those two things are involved. So you need multiple parts for there to be communication, right? And I find that is the definition that I have stuck to. It's not always a helpful lens, like you said, to look through things, but sometimes it can really be something that gives you a new perspective.
Right. And I think we've always talked about over-engineering. We've talked about that sort of thing. But I think that the nuance in a distributed system is the intent is, like you said, you want to maximize computational power by pulling upon different resources, truly resources, not people. But right. With that comes the overload of the heavier load of communication. and what amounts to the orchestration of the air traffic control, making sure all the pieces are in sync. You know, her Leslie's definition of distributed systems is like when I asked a developer once, what's the definition of a database trigger? And his Sean Martin, God bless Sean, his response was, imagine going into your kitchen and turning a light switch on, and then 4 houses down, the garage door goes on. And I said, oh, that's what it is. He said, yeah, it's just, don't do those. They're bad things. They're bad things. So when we think about distributed systems, Jonathan, so you and I come from large scale healthcare companies, which have remote workforces spread out across the country, if not the globe, right? We truly are functioning in what amounts to a distributed system, right? Lots of communication, lots of computation. What do distributed systems teach us about, like, things like coordination? What could we learn as humans from something that happens in a distributed system computationally?
So I think that distributed systems teaches us a lot about coordination protocols, like you talked about. Coordination does slow you down. Just like you said, it's an extra load. It's more cognitive load, especially on a team, right? But let's just stick with computers for a second, because they're much easier than people generally, right? So coordination slows you down primarily by adding delays, which are semi-artificial, right? Or they're sort of naturally implied, but artificial. It's an interesting, depending on your philosophical lens. So they add these delays that are required to get things in sync. And in computing, we see all sorts of instances of this. We see locks, we see consensus algorithms, we see replication delays. Sometimes you're getting in the way of the speed of light, right? It takes a certain amount of time for an electrical signal, even via light, right? Fiber optics or whatever, to be relayed from one side of planet Earth to the other side of planet Earth. And that delay, you're butting your head against physics. Don't try and fight it, right? So what are those delays? What is that actual communication aspect of the computation piece, right? What does that other part tell us? And it tells us that coordination protocols slow us down. Great examples of this, computer science has a bunch of things, 2-phase commit, 3-phase commit, right? You have to sort of say, hey, everybody get ready. Okay, everybody ready? No. All right, wait a second. Wait till everyone's ready. Hold it. Wait till everyone's ready. Okay, now everyone's ready? Cool. All right, do it. And then you got to wait till everyone does it, right? And the problem there, there's actually numerous problems with just 2-phase commit. The problem there is that, Jay, if I send you a message, how do I know if it's just taking a really long time to get to you, or if your response is taking a really long time to get to me? Or how do I know if you've been hit by a bus and you can't text back, right?
Right.
How do I know? There's no way to know. It's literally pretty undecidable, right? There's a proof here and everything, right? About how do I know if you are functioning properly and there's just a delay, right? Versus if you're gone. Now factor that reality into trying to get everyone on the same page, all these different computers all around the world on the same page. Because when you're inside a computer, you're talking about delays of nanoseconds. When you're outside of a computer, you're talking about delays that could be milliseconds or entire seconds or even minutes, right? I mean, crazy long periods of time for a computer scientist. Now, an astronomer or a geologist or what have you would look at that time scale and say that is incredibly fast because they work on time scales of millions of years.
Right.
God bless them. That ain't me.
Right. It's all about perspective. When we're talking,
exactly, it's all about perspective, and that's when we see that to answer your question, the thing that we learn is that coordination protocols slow things down, which explains recent advances in distributed systems, like the CALM theorem, CALM, different types of programming models where it doesn't matter what order things come in, doesn't matter, you don't have to get everything in sync, because once they all come in, eventual consistency, these sort of different ideas are very, very powerful tools when you're reasoning about systems like this, Jay.
So I'm going to put the agile nerdery lens on that, right? So you're talking about the delays inside of systems, which can add up, and they add to communication problems, collaboration problems, consensus problems, like everything gets sideways. It's almost, not almost, it is the same thing as what we deal with when we try to build teams and teams of teams and teams of teams of teams, right? There's I forget the name of the law. I have it on a board somewhere. R equals N in paren n-1/2, right? The number of relationships in a system. So that's why you have teams that should really be 3 to 5, not 5 to 7. That's a different Agile argument podcast. But the more connections in a system, the more nodes in a system, the more connections you have. You add complexity, you add overhead, you add delays. And if anybody wants to go back and listen to the interview I did with the Standish Group, Jim Johnson from the Standish Group, around decision latency, the longer it takes to make a decision, the less successful you will be on average, right? So you have a lot of nodes talking to one another, the weight of coordination, that cognitive load, plus the fact that you're kind of slowing yourself down for the sake of slowing yourself down.
That is absolutely right. We have seen this in theory and in practice, that multiple members of a team or groups of teams, or just like you were saying, at different levels of the organizational hierarchy, conceptual hierarchy, there are natural effectiveness drops that occur due to delays and the like. And of course, the more, just like you were saying, the more pieces you have in play, the more communication and the more coordination needs to be there. That formula you mentioned, Metcalfe's law, is a fascinating, whether that's true or not is a really interesting discussion that's actually going on right now in the community of mathematicians and computer scientists. But I think it's perfect here, Jay.
It really is. It makes me think of whenever I have teams that, teams that get unwieldy, or teams where you can't maintain a connection with your colleagues. That's when they become unwieldy.
Yes.
And we could do a whole other conversation about how we have managers and managers and managers. And when you have like 60 direct reports, like, do you really have 60 direct reports? That's kind of insane cognitively. But so Jonathan, we're talking about complexity and coordination. And then I want to kind of ease this into a little bit of an aside. The idea of swarm programming, is that, and swarming, is that meant to try and assuage some of this coordination latency by having everyone literally look at the same thing?
So that's a really cool question. That the origin of this practice, just in case anyone's curious, is really extreme programming, where pair programming, two people sharing one screen, became popularized. And what the research normally shows is that it doesn't actually reduce your throughput that much. So most people say, well, two people working on the same thing means that you're going to go at half the speed. It turns out it's actually about 1.6 to 1.7. So there's a little bit of a drop, but the quality generally is much higher.
Right.
And that's just for two people. Then you get a group together, and I find that the elimination of those synchronization delays that we talked about earlier, right, they just compound, right? Because you all of a sudden, especially when you're starting a project or working on a really tricky thing that everyone has to understand, get all those developers looking at the same screen, get them coding together, right? You get in live action, in living color examples of places where more eyes mean fewer bugs, right?
Right. And I just, as you were saying that, Jonathan, I kind of just thought, the other benefit to swarming that, besides talk about, the old joke, none of us are as dumb as all of us. If you have multiple people from the same team working on the same piece of code, the same piece of functionality, right? Knowledge transfer costs go down to nil, because you're all literally, I remember we worked on that. Whereas if, right, typically in a lot of the dev shops I've worked in, a new request comes in and the first question that's asked is, who worked on this last time? Who built it? Do they still work here? Because the cost of waiting for someone else to come up to speed is not something that, right, wrong, or indifferent, is not something that typically our business partners want to bear. Whereas swarming, you're literally training everyone up around what's being written at the same time. It's anybody who's listening who's a dev lead, please let me know if you had an experience with it and it hasn't gone well, because I'm kind of curious. There's got to be another side of this coin that we're not seeing.
Yeah, so there are actually some of the best evidence for how to do this right organizationally comes from the world of education. One of my mentors, teachers, and friends, Dr. Stephanie Arzanetti-Height, Dr. Height just co-published a book within the last year or two about collective efficacy, specifically in the educational environment, and how things like goal consensus and getting everyone on the same page from the get-go and making sure that everyone's sort of pulling in the same direction. That research really highlights that there are things you can do to make sure that it goes well. I love your idea of getting some failure stories out there. It's just every time you have a pattern, it's also important to have an anti-pattern, so you know not just what direction to go in, but also what pitfalls to avoid. right? And that's where the wisdom of crowds obviously kicks in, which brings us back to swarming, right?
Right.
And one of the things that is really cool, and by the way, I just want to preface this with a quote by George Box, who I believe was a statistician: all models are wrong, but some are useful, right? When we talk about people pulling in the same direction, there is a simple swarming model that you can describe in plain English. I'm actually going to give you a variation on the one that's on the Wikipedia article on swarming, because I think it's really good. And that is, it's a 3-step process for how to swarm effectively, right? It's not about top down. It's about telling the individuals what to do and letting them figure out how to do it, right? And that is, move in the same direction as your neighbors. 1. 2 is stay close to your neighbors. And 3, this is the last one here, right? Avoid collisions with your neighbors.
Wow, that's really simple and elegant, and yet it really makes a lot of sense. No jargon. It just makes sense.
It's really cool.
That same concept, right? So stay close to your neighbors, stay in contact with your neighbors, avoid collisions. That is, Jonathan, keep me honest, that's the same kind of logic you can use when it comes to team interactions, departmental interactions, right? Like coordinating at scale, right? We many listeners of the show have heard that we do a lot of conversations around scaled agile framework and scaling agile. Isn't that just good? Like, I don't want to say it's the golden rule of collaboration, but it kind of is the golden rule of collaboration, right? Stay in contact, stay in touch, don't get far, don't collide.
I think that it not only, listen, back to your earlier point about individuals in a team versus teams of teams versus, groups of groups, et cetera, et cetera. I think that you're really circling back to what you said earlier in terms of the importance of looking at different levels of the hierarchy, and you pointed that out perfectly. And that is absolutely true. I don't have to keep you honest here. I would be really curious to see what different kinds of organizations think of that model. You obviously have more rigid, safe, like, let's talk about, scaled agile framework, right? Like you were mentioning.
Very prescriptive.
Very, very prescriptive. That's a great word. Very prescriptive, right? I challenge you to open up the Scaled Agile Framework website and time someone, how long does it take to find the customer on the full safe, diagram, right?
We should run that. We're going to do that as an episode. We really are, because I'd be really curious.
That's a great hallway usability test, right? Open this giant diagram that tells you how to do everything, right? From top down, right? And find how long it takes to find the customer. Right? Now, does that mean that a swarming model would find the customer faster? And that's not the comparison that we're making, right? The comparison that we're making is allowing people who are close to the problem to determine the solution in concert with one another based on simple guidelines. And that's how you get swarm behavior in ants. That's how you get schools of fish that work together. I'm obviously simplifying, forgive me. There's some really interesting examples from biology and nature out there. And my question is, why are organizations, and maybe you have broader perspective than I do, why are organizations so hesitant to learn from the things that are right in front of us?
If I had to answer that, if I'm speculating, I really think some of it comes down to fear. Some of it comes down to insecurity, right? Like, let's think about how the world of projects and standard PMBOK-based delivery propagated. It propagated because it helped people sleep at night. Whether what was on the plan or whether what was on the plan is realistic, or the delta between the plan and reality was huge, like Grand Canyon size, that didn't matter because someone saw a plan and they got comfortable with it. And I think that there's something to be said about looking at a big picture, looking at a massive diagram, or even having a consultant show you a big picture or a massive diagram and saying, here's where, you are. It's like a map at a mall. Those people who remember actually going to a mall, you are here. Yeah. I want to get there. Okay, well, I got to do this. So one of the things we were talking about, Jonathan, offline, and I'm going to bring it into the conversation. We've talked about, teams of teams. We've talked about the cost of coordination. We've talked about swarming. And you threw a word out there, which I had to make sure I was reading it correctly. Fracticality.
I've always read it.
Fractality.
Fractality. Right. That's how I've always read it. And by the way, that is a big word for Elmo. Let me just put that out there. Fractality. It's not the kind of one you want to drop into everyday conversation. The notion that like a fractal, when you zoom in, right, you see echoes of the whole. It's sort of this theory of reiteration, right? And when you zoom out, those structures remain. And you can zoom in infinitely, right, down to the individual level, or below if you are qualified to engage in such psychological analysis. I am not, right? But you can sort of zoom back out, right? Individual, team, department, division, even to firm and company, even to economies interacting. You can sort of zoom in and out, up and down this hierarchy. And yeah, I've found that if you're using models like these to analyze things, there is a certain level of fractality there.
Right.
A great example of this, if this is something that interests you, the complex adaptive system world is fascinating. I recommend that the Santa Fe Institute, they have some wonderful podcasts and wonderful introductory materials. Their books are remarkably cheap on Amazon and so informative. You know, pick one up from your local retailer. If you want a cheap ebook, that's fine. There's awesome stuff out there that can really, I mean, it certainly opened my eyes and showed me the more I learn, the less I know, which is a great feeling.
Yeah, I'm glad you brought up the fractals. You know, for those of you who have seen it, but Benoit Mandelbrot, right? Mandelbrot sequences, they look like kind of, somebody described it to me as a snowman with warts, the shape. Because because you zoom in and zoom out. Coarse grain and fine grain, the systems look the same. I know, like even ideas like Scrum at scale, it's based on fractals. So you theoretically can infinitely scale because you're aggregating and repeating repetition over and over and over. And I'm glad you brought the C word up, right? So shout out to the Complexity Institute. Shout out to Dave Snowden and Knevin and Cognitive Edge. Jennifer Garvey Berger touches this stuff. I love the Santa Fe. There was an episode with a woman who talked about ant colonies and how they do decision making and the role of generalists versus specialists. And I was kind of like, awesome. I almost drove off the road because I was like trying to take notes while I was listening. But let's go back, Jonathan, to the idea of a team, right? A team, technically, a team is a complex system, no?
Okay, so this is a really cool question that you're asking. I just want to make sure I understand it. Are you asking, is the landscape of individuals in a team a complex system, right? A complex adaptive system, or is it? Are you asking about teams in a group, or are you asking about both? Because we just.
I'm asking about just teams in general, right? Like, so teams exist in complex adaptive systems because all of our world is a complex adaptive system, right? Like, you want to talk about like infinite scaling, and here comes Mr. Gödel and the incompleteness theorem, which, by the way, did you know he starved himself to death? Did you know that?
That's wild. I didn't, but I'll tell you.
He used to take.
Mandelbrot, if you want to see some cool history, look him up too. Tell me what you were going to tell me.
All those mathematicians have interesting histories, but Gödel used to take walks with Einstein when they were at Princeton, and he apparently later in life developed a very, very deep-seated paranoia. Like, he was literally convinced that everyone was out to get him, and he starved himself to death. He died of wasting disease. But brilliant minds. But whatever. The other funny story about him is he showed up at a conference where John von Neumann was and a whole bunch of other mathematicians, and he started talking about his incompleteness theorem, and everybody basically tried to run him out of the room except von Neumann, who was like, ooh, come over here. Let's have this conversation because you're saying something that I don't think I get, but I think you're onto something. So long story short, when the smart people, unfortunately, really smart people look like crazy people to dumb people was the statement
That's great.
Was the statement I came across. So yeah, let's talk about as a team. A team itself is a complex system, right?
Yes. So let's take so let's take Scott Page, Professor Scott Page, his definition of a complex system, complexity, right? So a complex system, according to his definition, has 4 parts, right? So I hope I get this right. It's made up of connected entities, which are independent.
Okay.
And which are diverse such that they differ from one another on an individual level. You can distinguish between them and their different flavors of entities, right? Okay. And the coolest part is that which adapt both to their surroundings and to one another. So connected entities, right? They are interdependent, right? And they are diverse, right? And they adapt, okay? So if you want to look at, big systems here, you can look at traffic, right? You can look at banking networks. You can look at all kinds of other things. Love to see it, right? But you're specifically asking about teams. So, do they meet this definition? They're made up of individuals which are connected. That's true. They are interdependent. Absolutely. They are diverse. Absolutely. Well, I mean, I hope that they're diverse, right? Otherwise, you're going to fall prey to, groupthink, or what they call it in business school, I believe, is dominant logic, et cetera, right? You want to avoid that, which, by the way, is one of the reasons that I don't hire for culture fit. When I hire for values fit. I want you to bring something new to my culture. I want you to care about the stuff that I care about.
You can't hire the same. If you hire everybody who thinks the same, then you end up in what is commonly derided in public discourse today. It's the idea of putting yourself in a bubble where you're only surrounding yourself by people who think like you, who have the same social thoughts, and then you end up painting yourself into a corner.
Yes, absolutely. So exactly right. So your question, my answer would be that according to Scott Page's definition, absolutely. Now, how else do we know, other than it fitting the definition, how else do we know that teams are complex systems? Okay. Well, one cool thing that happens is when you have complexity, not just complicated, but actual complexity according to this definition, you get emergent behavior that comes about and yields significant novelty. That novelty can be measured by the degree to which it fits a normal distribution. If that's a valid assumption from the get-go, we can have an entire discussion about that with a statistician who would school at least me on that. So no, it's not normal, right? That emergent behavior is not normal. It doesn't fit to a normal distribution. Sometimes it's exponential behavior and it fits to a power law, right? But there's also some really cool properties that come out of complexity that we do see come out of good, properly functioning teams, right? Robustness, they can withstand disturbance. Typically, the more diverse your population in your system, the greater tolerance to disturbance it has. You can see non-linearity, which is really, really cool. A good example of non-linearity would be that the size of the output is not proportional to the size of the input. Okay. So that is to say, if you put something in, you get an outsized response, right, throughout the entire system.
Right, and getting away from the intellectual talk, like that would be something that a good manager would expect of their team, right? If you build a good team, the request goes in, and what comes out the other end, 9 times out of 10, should surprise you because you have brilliant people working together to come up with a novel approach to something, right? Your idea of novelty and the emergent behavior, right? That's what you would hope. You just throw it in there, and whatever comes out should be mind-blowing.
Right. Yeah. And that's why there is such power, again, to the collective efficacy aspect, but there's such power, not to be cheesy, but in people coming together, right? I mean, E.O. Wilson, the famous biologist, said one ant. Oh, you're going to have E.O. Wilson's book? Oh my God, you are the coolest. You are. How do you do that? You're so much cooler. Okay. Anyway, so he has this quote. Maybe you found it in that book. I don't really know where it's from, but one ant is no ant, right? They come in groups, right? And one person is no team. They come in groups, right? And you see that this emergent behavior only comes when you have multiple entities that come together. A great example, one neuron is not capable of consciousness. A whole bunch get together, cool stuff happens. Right. One car is not a traffic jam. You get a whole bunch of them together, boom, all of a sudden you're late for work, right? So these emergent behaviors come about just by nature of these independent entities coming together and working. And that's maybe the core learning, the core lesson that I have been reminded of the hard way, right? When I look at teams through distributed systems, right, through this lens of distributed systems, is that if you overplan, if you over-coordinate, if you over-design your organization, you end up clamping down on the complexity instead of harnessing the effects of complexity.
And that was going to be my question. Yeah.
Yeah, there you go.
Jonathan, how do we screw this up? How do we, and I mean the royal we, right? Like leaders, managers, agile coaches, org design specialists, how do we screw this up? What do we do that screws it up? What should we be looking for?
I honestly, in the studies that I have made, which are relatively informal, and I would love if anyone out there is an organizational psychologist who can point us to some research to, either confirm my hypothesis or, ideally make a discovery that it's wrong, which is the best kind of science, right? The things that I have noticed in my studies generally come about because of, as I said, over planning, over organizational design, too much coordination protocol, right? That is what introduces delay. Delay is, if you want to look at this through the Marion Tom Popendiak lens, delay is waste, right?
Yep.
In that sense. So you're sort of introducing waste into the system unnecessarily by overdoing it. I would love to see an experiment, and maybe this is the kind of thing we can do with multi-agent simulation software, right? Like NetLogo out of Northwestern. I think that's Ori Walensky, his research group. I would love to see, when you give a group of agents a swarming model, right? And then they self-organize into a swarm. If you then take a swarm of swarms, right? And what happens? I would love to see an organization adopt a simple enough, like you said, jargon-free, really relatable, understandable swarming model. Give it to individuals on the same team. Let them assemble together, right? Give that to teams in a division or in a department. Let them organize together, and so on up the chain, right? To let the people who are closest to the problems solve the problems because they have the best understanding, and let them make autonomous decisions by pushing that decision making itself to the edge.
Right. But let the decisions, it's the Peter Maurer calls it the doer decider distance. Shrink that to the point where the person who's doing it is the person closest to it, is the person should be deciding. So the other thing I'm taking out of what you're saying, Jonathan, if I'm a leader, right, or if I'm an executive, the other thing I'm taking from what you just said is we need to consciously design our systems with room to breathe. They need to be given a little bit of space in order to expand or contract or find their own center, right? And when you were saying that, here's the analogy that pops in my head because I read too much, right? C.J. Chivers is the war correspondent for the New York Times. He wrote this book titled The Gun, which is the history of, it was 3 parts, the history of the machine gun, right? The history of the automatic Kalashnikov 47, the most well-known prolific machine gun in the world, and then how it became so prolific. And when we talk about designing systems to breathe, he tells stories of American troops in Vietnam who had the Armalite AR-15, which is the M16 precursor, and the NVA was being supplied by the Chinese with the AK-47. And the Armalite would always jam. It would always jam. It was always screwed up. And the part of the problem was it was designed so tightly coupled. Here we go. Software architecture. It was so tightly coupled that the moisture and the humidity and the climate would interfere with the mechanism of the gun. The AK-47, however, did not have this problem. Now, everybody knows that the AK-47, you gotta be a decent shot to hit the broadside of a bus 15 feet away because it bounces all over the place. But the gun is designed to have that space. The studies have shown that you could take that thing and drop it in a mud puddle, pick it up, and the first round will actually clear the breach in the barrel. It's designed to be resilient because it, and they said, because it's got spaces, it's got room to expand and contract. It's not so tightly coupled. And the thing was, we have this M16, which is a good weapon, but the AK-47 is just that much more reliable. It was designed so you didn't have to maintenance it because it would sort itself out. And I think he's, not going to bag on it, but I think of some of the scaling frameworks we do, or some of the things that Agile coaches come around the corner and wave and say, we need to do this, we need to do this. Here we are lecturing about modularity in software engineering, but then we don't take that same approach with how we design organizational systems.
That's a really cool parallel. We can learn a lot from the phenomenon that we observe every day, not just a weapon finding its own way to expand and contract and find optimal equilibrium to maintain its function, right? That's a really cool observation. Another place that we can find that is actually the pro-democracy protests in Hong Kong. They can teach us a lot about system design and organization. I gave a talk at one point about system design lessons from the Hong Kong protests, and one of the things that we talk about in there, right, about finding the equilibrium, is that every system is going to have to find its own. And one of the reasons that the protesters were so much more effective than the police, especially in the early phases of that, was because they picked effectiveness over efficiency, right?
Right.
Okay.
Right.
And the police who were trying to crack down on these pro-democracy protests, right? They stuck to their strategy. They didn't change. They stuck to their tactics. They didn't change. They stuck to everything because this is the tactic that we are optimized for. So we're gonna fight it all the same way, right? We're gonna tackle the problem in front of us the same way that they always have, and they didn't adapt fast enough. So yeah, were the police on the macro level more efficient? Absolutely, but they certainly weren't as effective.
Yes. It's you talk about equilibrium and the idea that I think some of the things that we lose, Jonathan, as people, and this is going to be a little bit of a rabbit hole, but I'm not going to take us down. I'm going to give you a glancing blow and move us along. I think some of the problem that we have with some of our organizational systems, our political systems, our structures, is we design them like they're machines, and they're not. They're organisms. They're organisms, right? So the idea of homeostasis, where a system left to itself will find a way to meet its own equilibrium, right? Like the idea of low entropy and high entropy systems. It's like when you sit in a chair and your butt is warm and the chair is cold. Over enough time, your butt and your chair will equal the same temperature because it reaches an equilibrium. And I think, to your point, when you commit to one side too far, you remove the ability to seek that homeostasis, right? Like it's funny you mentioned the Hong Kong protesters and the police and how they stuck to a plan. I just finished Adapt by Tim Harford. And he talks about the importance of evolution when it comes to successful system design, organizational design. And he references Peter Polchinski, who was this Russian engineer who was around for the czars. He was a Trotskyite. He was around for the revolution. And the Soviets hated him. The communists hated him because he was brilliant. And they would say, how do we fix this? And he would go in and he would look and he would say, well, here's your problem. But he never gave them the right answer. So they would send him to a gulag. They brought him back. They did this 2 or 3 times and they killed him. And then they eventually killed him because he would not admit to whatever he was charged with. But his thing, when we talk about complex systems, when you talk about organisms, evolution, he had 3 principles, which I think makes sense here. His first principle was variation, right? You need to try different things. Consistent experimentation. Yeah. This is where you give the system room to breathe, like we talked about. The second thing is survivability. Whatever experiment you do run, you need to be able to survive it. The operation cannot be successful, but still kill the patient. And his third thing was selection. When you find what works, you need to use that as a new model and test that against all these other things in combination with other things, because then maybe you'll find an even better solution, which is how nature works, which is how you and I are sitting here, and we're not, just bears with opposable thumbs, because that's really what guys are anyway. Jonathan, I want to go back to very early on when you did your introduction. You talked about the actor model, and I'm not even so sure I get it. I think I do. Can you explain to us a little bit about the actor model, and then how it ties into the book you're writing?
So yeah, when we talk about the cooperative aspect, right? The actor model does become relevant. So a little bit of history. The actor model is a model of concurrent computation, right? So computers doing more than one thing seemingly at the same time, right? It has been extended to true parallelism, where they actually do things at the same time. And actors, this model of concurrent computation, it was developed primarily by Gul Agha when he was working on his PhD in Carl Hewitt's research group at I'm blanking on the university. And basically, the whole premise is that every piece of the system is an actor. It's this primitive notion. And what is an actor? Well, it's anything that obeys the 3 actor axioms, the laws of actorhood. Okay, so law 1, it has to have communication, which is specifically the ability to send and receive messages. So an actor can send and receive a message with other actors, right? So let's say I'm an actor, you're an actor, I can send you a message, right? Okay, cool. State, which is the ability to remember things such that the reactions for subsequent messages are altered, right? So let's do a quick example. I'm an actor, you're an actor. Jay, remember that the magic number is 3, okay? Okay, what's the magic number?
3.
Okay, well, you remembered, right? So therefore you have state, and that altered the answer to a subsequent message, right? So that's number 2. Number 3 is replication, the ability to spawn or create more actors, okay? So if it has communication, memory, and replication, it is an actor. Now, this should sound a lot like a very general, non-specific model of human beings. I can't control you. I can send you a message in various forms and ask you to do something, but ultimately it's up to you whether you do it. I can't reach into you and mess with things, right? However we want to do that. So the actor model, which I'm writing my book about with my colleague Matt Ping, who is wonderful intellect, great person, brilliant practitioner. The actor model became hugely influential in computer science in various circles, and specifically distributed systems research, because there's no requirement that actors execute in the same place or at the same time. So all of a sudden you can have, it's really cool. So all of a sudden you can have two actors passing messages, and they're running on different computers in different data centers on different continents, or however you want to do it. And then you get back to, my crappy definition of distributed systems, which is communication, talking, and computation, doing things. Okay, so this is a really cool way of modeling concurrency. Programs doing more than one thing at once. I find that the normal, traditional, threaded model of programming is a poor metaphor for concurrency, in addition to being confusing as all hell, at least to me. Right? There's so many bugs in this. The actor model takes very different approaches, and you will find that the software systems that can produce actual operational software that has the highest uptimes, the highest resilience to failure, they use the actor model. Erlang, which was invented in the 80s by Ericsson for programming telephone switches, great example. The new programming language Elixir, which is built on the same platform as that, makes that that whole swath of functionality, really resilient, fault-tolerant systems using actors, much more accessible to certainly me. And yeah, I mean, my job is to build imaginary objects for money, so I find this stuff incredibly useful, right?
I've never heard development referred to that way, but it really kind of is. These ephemeral imaginary objects for money.
Yeah, and weirdly they pay me, which is really cool. So this actor model. I found that when I was talking with my co-author Matt Ping, I found that the literature, and Matt agreed with this assessment. The literature tends to fall to two extremes. Either the actor model literature is very, very abstract, right, and really primarily useful in an academic context, or it is very implementation specific. So it will say, this is how you solve this problem with the actor model in this programming language using this library, right? So there's nothing in between super abstract and super specific. So one of the things that our book tries to do is it tries to take the patterns that we find and show them in terms of actors, but using a variety of different programming languages to get the concepts to stick as best we can, and make it appeal to as many people as we can find, right? Obviously, it's an imperfect parallel for me to draw, especially when it comes to supervision trees and error handling. It sort of flies in the face of the swarming discussion that we just had and the value there. But software systems and organizations are very different in a lot of ways, as much as we can draw parallels. Like you said, they're a little bit more like organisms. I really like the biology metaphor. I like that a lot.
Yeah, you're going to be hearing more of that soon. So let's talk about Jonathan. Let's call back to the episode we did with Mark Burgess and promise theory, right? So if you have a bunch of actors working in distributed systems, right, where they are residing in distributed systems that reside in a complex adaptive system, right? Here we go, inception, multiple levels. So this is where things like promise theory come in, right? Where two people agree that I promise you that I'm going to deliver this. It helps aid in the idea of convergence, where we're converging on something versus we talk about what we kind of need. And then we, as anybody who's been in software development in the enterprise for more than 15 minutes knows, you wildly diverge. And what I wanted the rack of lamb and I got a Wawa sizzly, it's typically what happens.
Yeah, I think that promise theory is a really cool adjacent topic to this. And Mark Burgess has written extensively on this topic, both for computer scientists and mathematicians to look at, as well as people in business and people in technology, especially. Promise theory is a really cool alternative to a lot of the obligation logic. So we tend to think of how do I want to say this? We tend to think of command and control systems as primarily being about imposition, right? As opposed to flipping this on its head and saying, well, I'm not taking orders, I'm promising to fulfill this this
request,
prompt, right?
Yes.
I'm saying exactly, right? So it sort of puts the, philosophically, you may say that it puts the onus on the individual to actually do the thing that they're supposed to do. And that's a really cool concept. Highly recommend that you, any listeners who are out there, check out Mark Burgess's work. Maybe listen to that episode. He was really erudite in a lot of ways. Certainly gave me a lot to think about.
Terrifyingly brilliant. Yes, terrifyingly brilliant. So, Jonathan, we've talked about distributed systems. We've defined them. We've defined the actor model. We've defined complexity and how all these things are complex. Let's go a little bit off the beaten path and talk about hierarchy, and hierarchy specifically in regards to organizational structure vis-a-vis some of the there's thought models out there where you want to totally blow away all of your hierarchy, right? Things like sociocracy, things like holacracy,
right.
Things like
right.
there's another one where it's just a massive re-leveling. Now I got to interview Brian Robertson. It was really kind of fascinating, his thoughts on holacracy. I'm still on the fence. I'm not sure if these type of ideas would work, seeing how humans are, right? Like that's the thing I keep butting my head up against. What are your thoughts?
So my thoughts are that I don't know if the theme of this show, teams through the lenses of distributed systems, I don't know if distributed systems has an answer to your question, right? And I can tell you that I certainly don't have an answer to your question. I think that a lot of it is dependent on culture and sort of, I'm going to give you a typical computer scientist answer and say it depends, right?
Which is also the Agile coach's default answer, by the way. So you're in good company.
Cool.
This is what, when you don't know, pull the ring in the middle of my back and I just yell, it depends. And then there you go.
Right. there you go. Right. So and there are people who have thought and studied this far more than, certainly I haven't. It's not, it's not my area. You mentioned Frederick Laloux's book, Reinventing Organizations, and his classification system based on color, which, has some really interesting strengths and weaknesses. You mentioned holacracy and sociocracy. I guess I would answer your question also with a question. I would say, which pieces of human nature do you find to be obstacles to adopting a lower hierarchy model?
So Jay, the social scientist here. I missed my calling. I shouldn't be a podcast.
Love it.
I guess my paramount objections are one of, when you look at human history, right? And when you look at the authors who write books on things like mega history, right? Your Jared Diamonds, your Yuval Harari, your Peter Turchin, and they talk about viewing history through the lens of all of it. And one of the things that led us to be the perfect apex predator on this planet is our ability to collaborate, simple tools, right? Thumbs, simple tools, collaboration, networking across large groups, right? It's truly a distributed system is what allowed us to invade Australia and kill off all the megafauna, for example. But I do think there are some parts of humanity where we do have that innate concept of a pecking order, right? Howard Bloom talks about this in the Lucifer principle, where there is some concept of a pecking order, and whether we like it or not, it's almost a natural fit for us. And let's call back to E.O. Wilson. He said that we are primitive creatures operating in a Victorian system of society with godlike technology, or something to that effect. But our brains have not. When you take your mammal brain. You take it with your baseline brain, right? Your the back part, right? I forget. I'm totally blanking now, right? Your lizard brain, your mammal brain sits on top of your lizard brain, and then your human brain sits on top of your mammal brain, and that is the least evolutionarily advanced part of us. We're always going to go back to that mammal part, the triune brain. We're always going to go back to the mammal section and the lizard section, which is telling us there is some sort of hierarchy. So that's where, maybe I should call Brian again and have him come back on to talk me through this. But I really do think maybe we need it, or maybe we don't need it. I don't know, but I definitely can tell that humans feel comfortable, and generally we feel more comfortable. We know that there is some sort of who is in charge, right? And so maybe at this point, maybe the most brilliant people on the planet are all of our religious scholars, right? Because they literally know who's in charge, and they just truly have faith that there is something up there. I don't know, but I think human nature, and our need to know that someone is planning or in charge because it adds safety and adds stability. I kind of think that's what gets in the way. And maybe it is just an evolutionary thing where our brains haven't caught up to The mammal part hasn't caught up to the human part, or vice versa.
So, I am reminded when you're talking about human nature, and especially in the context of, a very stark right and wrong spectrum, I am reminded of a book by the Egyptologist Kara Cooney that came out probably within the last year, called The Good Kings, Absolute Power in Ancient Egypt and Today, and Modernity, or something like that. And in this, Dr. Cooney, she speaks extensively on the rose-colored glasses with which we view ancient Egypt as this, as this wonderful society. And she talks about, through analyzing the reigns of different pharaohs, this is pretty cool, like what life was like at various different levels of society. And if you were at the bottom, it sucked, right? And that was horrible, right? And we don't want that in our companies today, right? We don't want that we do not want to be ruled by a pharaoh. My people were freed from pharaoh. It was not good, right?
Right.
Thousands of years later, we still, have a big dinner and remember it, right? We have a lot of learning to do, I think, in terms, and this is just me talking here, right? In terms of the way that we treat one another, in terms of speaking to one another with compassion in the workplace, showing kindness, and really that cooperation, that understanding of one another and diversity and differences, that is what allows you to move in the same direction as your neighbors. That is what allows you to stay close to your neighbors. That is what allows you to avoid collisions with your neighbors. And I really, this book is really cool, and it, in certain ways, it definitely speaks to your objections, right? It definitely strengthens the argument of your objections there. Right now, I'm not sure you could establish an Egyptology nerd to computer scientist pipeline, but
hey, stranger
that
things
is
have
certainly that is certainly the path I took, man. I once turned in a homework assignment written in hieroglyphs, and I thought it was dash clever. My teacher did not.
I would have given you the A. If I was the instructor, I would have given you the A, because it takes chutzpah to do that. So I was like, hey, anybody who's got the stones to pull that off, go for it. So Jonathan,
eighth grade me did not have you as a teacher.
Even better. Yeah. Eighth grade, even better. So if we had to summarize, so we've covered a whole ton of ground. If we had to summarize all this into like a thesis, like if you were giving instructions to all of our listeners, right, all the people who are listening regarding, looking at teams through the lens of a distributed system, what would that core thesis be? Like, how would you summarize this conversation?
I would say two things that are based off the learnings and the parallels we can draw with various distributed systems research. I would say that, one is centralize sparingly and deliberately, intentionally, right? If you're going to centralize something and remove people's autonomy in any way, whether it be choice or freedom to act or whatever it is, centralize only as you need to. And then I would go back to something I said earlier, which is, as a core thesis, don't overplan, overstructure, over-architect, or over-specify your systems, whether they be organizations or software, right? Don't do those things. Don't overdo it, because you'll end up sacrificing effectiveness in the name of efficiency, right? And I think that is the hardest thing to resist doing for many organizations, is to, your big design up front, right? Your in terms of software architecture practices and all these other things. And it plays right into the basics that the Agile community has known about for a long time: sense and respond over command and control, all those sorts of things. So yeah, don't overdo it, right? Guide with an easy hand. Don't play too close, right? Give people the freedom and trust them. I mean, and I'm not saying anything that I'm sure previous guests haven't said, but hopefully it does reinforce the importance of those relationships and the people that you're with.
Perfect. So Jonathan, if someone's checking out this episode, they want to find you, they want to get in contact, they want to ask you some questions, maybe pick your brain, where do they find you?
They can absolutely find me, I think, on the Twitter, the bird site is how many people find me. I'm also weirdly Googleable. My handle everywhere from IRC to Twitter is Yonkeltron, YONKELTRON. Tron. And I'd love to hear from you. I hope it's clear that I love this stuff and would love to nerd out with anyone who wants to nerd out with me. So consider this an open invitation to continue this discussion, provided that you can teach me half as much as Jay has taught me in the many years of our friendship. So thank you.
Please, you're flattery. So on behalf of myself, I want to thank Jonathan for taking time out of his evening to come and have this conversation. We've been scheduling this and moving it around for quite a bit, so it was awesome to finally do it. On behalf of Jonathan and myself, I want to thank all of you listeners for tuning in once again. If you enjoyed this episode, give us a review, a rating, comment on your podcast platform of choice. It does help others find us. We do have a very vibrant Discord server. Yes, Discord. It's not just for video gamers and crypto bros anymore. So if you want to come in and have the conversation, we talk about all of our episodes. We go down the rabbit hole. We talk about books. We talk about classes to take it. I really do suggest if you want to get involved and meet some really interesting people, definitely do that as well. And lastly, we are committed to always being free. However, we do have a Patreon. And we also have a quarterly award Patreon level. So once a quarter, we send out gifts. Last quarter it was socks. This quarter, I don't know. Maybe I'll send my autographed copy of Adapt with all my notes inside of it by Tim Harford. But we do offer that as well for people who like the show and want to support and offset hosting and production costs. So once again, on behalf of Jonathan and myself, I want to thank all of you for tuning in. And until next time, this is the Agile Uprising podcast signing out.